Hello students, let us discuss about the relationship between the applied voltage and the width of the depletion layer. Consider a silicon diode. You know very well that for silicon diode the voltage required to break this depletion region is 0.7 volt, that is known as cut-in voltage or barrier potential. So here the diode is forward biased. So what is forward biased? So here it is a p-type side and n-type side. Your p-type is connected to higher potential and n-type is connected to lower potential. Your p-type is known as anode side, your n-type is known as cathode side. So whenever the anode potential is greater than the cathode potential is known as forward bias. Now I am applying 0 volt. 0 volt means it is an open circuit, so nothing will happen in this structure. The depletion region is not broken. Now I am increasing the voltage from 0 to 0.2 volt. Now the depletion region is not broken, but the width is considerably reduced. Now look at the previous case. Previous case, this is the width of your depletion region. Now it is reduced. If I increase the voltage further, what will happen? The width is further reduced. If I apply 0.7 volt, then the depletion layer or the depletion region is almost vanished. So your diode is ready to conduct. So your electrons are ready to conduct, or your electrons are ready to go from N side to P side. If I further increase the voltage, so this is a cut-in voltage, so voltage required to break the depletion region. If I apply 0.7 volt, this 0.7 volt which is used to kill this depletion layer. So that is a cut-in voltage or forward breakdown voltage. So for silicon diode, cut-in voltage is 0.7 volt. For germanium diode, cut-in voltage is 0.3 volt. And if I apply 0.8 volt, what will happen? These electrons, it will cross this region because there is an absence of depletion region. It will reach this positive terminal. So this is your electron flow direction, but we know very well the conventional current direction is always opposite to the electron flow direction. So the current direction we represent in this from P to N, but the electron direction will from negative to positive. So here depletion layer is completely vanished, so diode will start to conduct. So across the diode, if you measure the potential, you will have 0.7 volt. So but always there will be a 0.7 voltage drop across the diode. This is known as on state voltage drop. Now there is an electron flow. The electrons are flowing from N type to P type. It means your diode act as a on switch. So during on state, there will be a voltage drop across the diode. This drop is known as on state voltage drop. So this is the forward bias. Assume the anode potential is VA, cathode potential is VK. So what is forward bias? Anode potential is greater than the cathode potential is known as forward bias. That means your anode must be more positive when compared to cathode potential. So VA greater than VK. At this time your diode acts as a on switch or closed switch. When you plot the VA characteristics of silicon diode, so this is the circuit for plotting VA characteristics of silicon diode. Your anode is connected to high potential, cathode is connected to low potential. This voltmeter measures the voltage drop across the diode, and IAK measures the anode to cathode current. It measures the current. When I apply 0.1 volt, there is no current. 0.2, 0.3, 0.4, 0.5 up to 0.7, there is no current flow in the given circuit because still the depletion layer is present. After 0.7, if I increase the voltage to 0.8, what will happen? The current starts increasing. So this 0.7 volt is known as cut-in voltage or forward breakdown voltage. We call it as VBD, breakdown voltage. So diode is a non-linear device. What is non-linear device? Because we are applying some voltage, but here the current is 0. So here there is a non-linear relationship between your voltage and current. In this region up to 0.7 volt, your diode behave as a non-linear device. So the remaining thing we will discuss in the next class. Thank you.